Hey everyone, welcome to the first day and first talk at Demuxed. I am excited to be here. Today I'm speaking about budgeting Bytes, how we mastered cost-efficient storage at Vimeo. But first, let me take a couple of moments to introduce myself. I'm Tanushree Nori. I've been applying ML to problems at Vimeo for 4 years now. I'm also trained in Indian classical dance and music. Think ballet, but from southern India. I dabble in pottery and gardening, but I seem to be firmly stuck at beginner level at both. Just last year, I moved from NYC to Vancouver, and I seem to have embraced all aspects of the Pacific Northwest lifestyle, the wholesome, the annoying, both. So yeah, I'll move on to the rest of my talk now. So as you all know, video data is massive, it's burgeoning. With improved quality, new formats, and AI contributing to new content being generated, we're seeing continuous growth. More so with this explosion, storage continues to be a serious cost concern. As an example, let's consider a media company that's storing about 100 terabytes of their data in Google Cloud Storage's most expensive storage tier, standard storage. So they're storing this 100 terabytes of data for $2,000 a month. They anticipated frequent constant retrievals, but what they saw was infrequent retrievals or scarce demand. Now, had they stored that 100 terabytes in a less expensive tier, cold line storage, they could have stored it for $100 per month. So in being unable to approximate the demand or retrieval on their content, they were overpaying by close to 95% on their storage costs, or close to $22,000 in excess of what they would have paid. So this problem, especially at Vimeo, can really scale to millions of dollars, these kind of efficiencies, because we tend to store data that amount to petabytes. So optimizing your storage at that point is less a nice to have and becomes a business necessity. There are a few ways you can think of optimizing how you host content. There's optimizing compute, where you choose the right cloud instances and scale intelligently. You can optimize content delivery, where you would strategically place content close to the users using CDNs. Or you could optimize storage, where you would choose the right storage class for the right content. And that's what we'll be looking at today. So I've been referring to storage classes and storage tiers. I want to take a couple of moments to provide a primer or a refresher for those who are familiar. We'll be referring to GCS, Google Cloud Storage's storage tiers, for the rest of this talk. And GCS has 4 storage tiers: standard, nearline, cold line, and archive. Think standard and nearline for content that you would want to retrieve frequently and you want to have frequent access to. They're expensive to store in and cheap to retrieve out of. Think cold line and archive for content that you would scarcely retrieve. It's cheap to store in, but expensive to retrieve. So the analogy of shipping options loosely applies, and I've borrowed that. So standard and nearline are like 24-hour delivery, 48-hour delivery options, and then you have cold line and archive, with archive being cheap to store in, slow to retrieve out of, like a package that's stuck in a shipping container in the Suez Canal. So just to kind of give you an understanding of the asymmetry between storage cost and retrieval for archive storage, a single retrieval instance can equal the cost of storing in archive for 100 days or so. Some crazy, ridiculous discrepancy like that. So you would only want to place content in the cold storage when you're pretty sure that the demand or retrieval of that content is going to be less. So yeah, the key to optimizing storage then ends up being a balancing act. You don't want to pay for expensive storage when your content is rarely retrieved. You also don't want to pay for cheap storage and then be hit with massive retrieval fees. So it ends up being a balancing act between storage costs and retrieval costs. So at Vimeo, we built a policy calculator that the goal of which was to determine how much time should a video asset or an object spend in each of these storage tiers that we discussed. So the outcome would look something like you see in that timeline. For a single video, what is the recommended time it should spend in standard? When should it transition to the next storage tier nearline? And then when should it move on to colder storage tiers? So that kind of policy is what we were hoping to arrive at with this calculator. How the calculator works, you can maybe for now just ignore the gnarly equation at the bottom, and if you just focus on the top, we modeled the storage cost for all videos, factoring in 3 broad factors. You have the storage costs for each of those tiers. You have the retrieval costs based on video demand. You have deletion penalties if the video is moved or deleted prematurely. And then, of course, the size of the video itself. So all these components constitute what you would define as the cost of storing a single video through different tiers. So by aggregating this equation across all the videos that you're considering, you could solve this as an optimization problem with the goal to find the lowest cost for all videos. And so the policy that gives you this lowest cost would be the winner. We don't brute force through random numbers to solve this equation. There is a directed search, and there are a couple of methods to do that. I'm not going to get into that right away, but it is a mathematically driven search, and there is a method to the madness. And for any optimization problem, you will be bound by some constraints and assumptions. The few simple ones we've made here are that the policy that you would devise would be applicable uniformly to all the videos. And the second thing is the retrieval that we plugged in blue above would be the average retrieval for all the objects that are being considered. So you're working with expected demand and not the individual retrieval of a specific video asset. And yes, and then you aggregate this equation and you solve for it like you would any mathematical equation. So I just want to also show the journey of a single video under 2 different policies. For this specific video, you have the policy in blue, which transitions the video from standard to nearline, and then an alternate reality in which the video is transitioned into cold line also. So you notice that the green policy accrues lower costs because in reality, the video noticed low retrieval. And that therefore, it makes cheaper storage more cost effective. So all in all, with this simple approach, we were able to save close to 60% in our storage costs. And this method works especially well in homogeneous buckets, meaning where the common denominator is either region or upload source. It also works pretty well when you have a set of videos that are all raw video assets, where typically retrievals tend to be quite low. But what if we wanted to get a little bit smarter and tailor the storage policy for every individual video? That's where ML comes in, machine learning comes in, which we'll dive into next. In shifting focus to the ML approach, I just want to compare and contrast the differences in the outputs between the calculator we just saw and what we're going to see now. So with the ML approach, what you now have is a binary class or a binary label for each video asset. The label would indicate cold if the video is a right candidate for cold storage, and would indicate hot if the video is better stored in hot storage, so standard or nearline. In this pyramid that you see here, I've broken down the ML process into a set of steps. At each step, the complexity in data keeps reducing, and I'll start with the first step now. So you have data collection that's at the bottom of the pyramid. It all begins with gathering 90 days of data for each newly uploaded video following upload. At this stage, the data is usually raw, unprocessed, messy, and tends to be large in volume, typically. And the next level, you have feature engineering, where you extract key features from the raw data. So you condense all the information from raw data into a set of meaningful features that you then feed into the machine learning model. At the third level, you have the model training, where you have a trained model that has been trained using historical data patterns on a specific subset of videos and is now able to provide clear labels of hot and cold when it encounters the video asset. Then you have the prediction and classification step, where for a new, previously unseen video with 90 days of retrieval patterns that we've collected and engineered features out of, you get a new label using the model. And the label would indicate hot or cold. And based on that outcome, you would take a decision. Should that video be moved to cold storage right away? For the videos that remain in hot storage, you can choose to have a storage policy similar to the one we saw with the calculator. And the storage policy can stipulate a time period after which the video could be transitioned to cold storage. So this would kind of be a catch-all storage policy to move all content to cold after X months based on analysis, where you would notice the retrieval tends to taper. Now let's talk about data. Collecting data from the right pertinent sources is critical for this or any ML problem. And for this problem, the raw data came in primarily from two sources, CDN logs and origin server logs. With CDN logs, you have features like CDN hit rate, average CDN latency between requests, CDN error rates, and you also have popularity and view metrics, which are helpful, like the view interaction metrics. Referral source are the views coming in from like Twitter, LinkedIn, like Instagram, what have you, video retention rate. So all of these tend to give you a sense of demand, popularity, access, frequency of access, all of those critical features. And then, though less impactful, you also have user metadata and clip metadata, which can offer exploratory insights that give you an insight into the broad patterns in your data. Like, for instance, you could use user metadata and clip metadata to aggregate clips by certain user attributes or clip attributes, which can then help you maybe find distinct clusters of videos. So that would help you by giving you a choice as to what level you want the prediction at. Do you want it at the level of a single video? Do you want it by these clusters? So yeah, user metadata and clip metadata can also offer really useful insights. Feature engineering, the step 2 in our pyramid, is at the heart of making the system work. It transforms raw data into meaningful information for the model. For example, you have decay features, which give you a sense of how engagement decreases over time. An example is viewership, drop-off rate. You could think of other examples like the half-life of a video. You could define a metric like how many unique views in week 1 after upload over unique views in week 2. So things that help you get that sense of decrease in engagement over time. You have moving averages, which help you, smooth out volatility in time series data or video access patterns over time. So think 30-day moving averages or 7-day moving averages. So they help reveal patterns that a single snapshot might miss. And then you have, we used AutoMLs, which is automated feature engineering, libraries that allow you to automate parts of the process. So with AutoML, you are able to automate this sort of feature engineering component, which then reduces the manual effort of doing that because the library kind of does some of that for you and then also suggests features that are most predictive. You don't want to rely solely on this because these libraries would lack the domain knowledge that you possess, and also they tend to also run into the risk of overfitting for the goal. And lastly, we have custom features. These custom features were created in response to error analysis that we'll go into a little bit later, and the iterative process of improving classification performance. So we'll touch on them in just a bit. The next piece of the puzzle is ground truth labels. It's what you would need to train your model to be able to discern hot from cold. So with the classification problem, like distinguishing between dogs and cats, the labels tend to be static. But here, the labels it's not quite as simple to tag a video as hot and cold. You need to kind of dynamically assign these labels, and here's how we did it. At the very first step, you can start by analyzing 2 years of video data. You focus on access frequency, retrieval costs, storage costs. And then from this, you would get a base probability in step 2. And this base probability tells you how often is cold line storage cost effective for videos on average. So it tells you how often cold line storage is cost effective, meaning how often is storage cost less than retrieval cost. And then you have to adjust this probability with an adjustment factor. And what you would need for that is how often the video was retrieved and how recently it was retrieved. So you would engineer features with those factors, how recency and frequency, and create an adjustment factor that you would multiply with the base probability to then get an adjusted probability. And then at the final step, you would threshold this adjusted probability to get your labels, hot and cold, which you would then use those labels to train the ML model. So this is just a quick view of our results. We had promising results with our recall and precision. So with recall, what that means is out of all the cold videos, how many did we properly identify? And precision is of all the videos we identified, how many were accurately identified as cold. So it's kind of an assessment of quality. So both of these metrics were respectably high as a starting point for us. But of course, mistakes can happen. So what if we get the classification wrong? What if a video that's sent to cold line ends up being accessed more frequently than anticipated? So that's where error analysis comes in. There are 2 possibilities. You have the one on the left, where you see kind of a sustained increase in popularity, and the one on the right, where you see like a sudden spike, like a virality spike, and then it damps down. The one on the right would be harder to predict, and it's really, there's nothing you can do about it. You just assume that with your overall net costs through your model being overwhelmingly positive, you just let this go unaccounted because there's really no way you can predict these rare instances of virality. But the case on the left is interesting because digging into these examples where we did get it wrong, where we did misclassify, helped us figure out at what stage we might need to make improvements. Do we need new features? Do we need to parameter tune our model? Do we need to choose a different classification model than the light GBM that we chose? So it kind of helps you get a sense of how to adjust your model development process and can finish the loop following error analysis. So with that, what you see on the left, I know the y-axis is kind of hard to discern, but what that shows you are features that were most predictive in our classification model of predicting hot videos from cold videos. And a lot of these features were created in response to the error analysis process, where we really dug into the videos we misclassified, tried to see what they had in common, and we created a couple of custom features like when was the first access, how soon after creation is the first access occurring, or what is the average number of days that pass between the first and the last access, counts of peaks and valleys across different features. So a lot of these we noticed that a lot of the features which kind of captured those early activity indicators or different ways of summarizing frequency of access and periodicity, those tended to be the most useful. So with this additional improvement of predictions by video data instead of like a blanket bucket-wide policy that we saw in the calculator, we noticed an additional 30% increase in 30% reduction in how much we spent on storage. So that sort of wraps up the story of how we tackled cost-efficient storage at Vimeo. Thank you.